Welcome back to the second video about the details of the QMC5883L 3-axis digital magnetometer. In the first video, we had a detailed look at all its registers that you can read and write via I2C. We also came up with an architecture for an Arduino library interfacing to that thing, and we took the first steps implementing that library. That is, we wrote the code for the I2C communication as well as reading and writing its control registers. Card here, link in the description. I promised you that this time we would read out every last byte that we can get from its control registers, and we'll start out with exactly that. However, afterwards I want to experiment a little bit with the interrupt data ready output of the QMC5883L and try to optimize the communication between the Arduino and that chip using some interrupt routine. Enjoy! So let's just dive in directly with the second version of the code that actually reads all the registers, the QMC5883L version 2, link in the description. Of course, we have some additions to the header file of our library, and I also made some minor changes. We have a new typedef struct raw data access here, containing 3 integers x, y, and z, which will hold the raw data returned by the chip for the 3 magnetic axes. I also have a typedef struct raw data array here that holds basically the same data, but in an integer array. Your choice. The typedef enum error has been extended by another member, QMC data overflow. That's the error returned by the chip when the magnetic sensors are out of range. Besides our read config function here, we now also have a read data, a read status, a read temperature, and a read period. Details about all these functions when we have a look at the CPP file. Consequently, we have a whole new bunch of data retrieval methods to get data from our object after we read it from the chip. And we start off with the raw data stuff for the 3 magnetic axes. No get set here because, remember our architecture, these registers are read-only. We start with raw data axis, which just gets the index of an axis between 0 and 2 and returns the integer value for that axis. Then we have 3 methods here naming explicitly the axis, and then we have raw data axis respectively array returning a raw data axis respectively array struct. Then we have retrieval methods for the status register. That's also read-only, so no get set. And we have here only our 3 status bits: data ready, data overflow, and data skipped. We have, again, read-only register, a raw temperature method here, returning us the 16-bit value for the internal temperature sensor. And we finally have here a get period. That register, the period register, is read-write, so we have get and maybe later on a set method here that returns just the content of that register. In the private section, we stumble about the first change I made. I now initialize all my static constants here within the header file, no longer within the CPP file. There's a reason for that. Just wait a second. We also have a new static constant here, period register default. More about that in a minute. And here's another, the second change. The size of my registers array is no longer hard-coded, but I take now the last register, the period register +1. And that's also the reason I'm initializing now all my constants here in the header file. Because if I initialize them in the CPP file, I cannot use them as constants in my header file. In the CPP file, we have another change, the third, and it's in our reset method. But before we have a look at that, we have a peek into the datasheet. In the first part, I told you I cannot find any information about what that period register exactly does. However, it was recommended to write a 1 into it. And within the application examples, here the continuous mode setup example, we find a line write register OBH, so our period register with 1 defined set reset period. And indeed, if you don't write 1 into that register, the chip doesn't work properly. At least I found that you might get magnetic readings from it, but for example, not the temperature readings from its internal temperature sensor. We still don't know exactly what that period register does, but anyway, within our reset method, I'm now setting that period register to 1, the new constant, period register default, and I'm writing it to the chip, and everything seems to work fine. So, the new methods. First of all, read data, and I'm reading here all registers, all 6 data registers, plus the 7th status register from the chip. Of course, I exit the function and return false if that fails. And I check within the status register that bit data overflow, and if that's set and our magnetic readings are off the scale, I set my last error here to QMC data overflow and also exit the function with false. Otherwise, I exit it with true. Read status is a simple affair. I just read the status register, and the same holds true for the read temperature, where I just read the 2 registers holding the temperature. And finally, we have that read period that just reads the period register. Then we have our raw data access function here that does the heavy lifting for the magnetic data. And it gets, remember, as an argument, the axis as index between 0 and 2. And I have here my base address of my register array. I add to that the address of my data registers, and then I add 2 times the axis. So I shift by 2 bytes through my data registers here. And I tell the compiler I'm pointing here not at a byte, but at an integer 16, and I return the content of that address. Raw data X, Y, and Z, just use that raw data access function here. And raw data access uses this raw data access function to fill up a raw data access struct and return it. And the same holds true for the raw data arrow, which also uses these functions, but this time to fill up a raw data array struct and return it. We have our status register bit functions here, so data ready, that's just the status register binary ended with the bit data ready. Same holds true, of course, for data overflow and data skipped. And return raw data uses the same technique as the access thing. We have here our register plus the temperature register offset, and we tell the compiler it's a pointer to a 16-bit integer, and we return the content of that address. Get period just returns the content of the period register. Fourth and last change in respect to the previous version. Here in the read registers method, I'm now checking 3 times if we really get the expected number of bytes back from the chip. So remember, I already checked that in request from, and when we read the bytes from the input buffer of the wire object. And now in between, I check again for that with wire available. Me being paranoid. That's all. The sketch itself. I considerably trimmed down the setup. I of course still do a begin, and if that fails I print out the error. I still set the config and its mode continuous, output data rate 10 Hz, full scale range 2 Gauss and oversample rate 512, interrupt disabled false, and then I write that config, and if that fails I again print out the error. And that's it. In the loop, something is going on now. I have a delay here of 25 milliseconds. Remember, we have a 10 Hz data output rate, so every 100 milliseconds measurement from the chip, I print an empty line. Then I read the status. If that fails, I print the error. Then I print the status, I read the data, and if that fails I print the error, and then I print out the raw data from my 3 magnetic axes using the raw data access method here. And then again I print the status. Remember, read data also reads the status byte. Then I read the temperature, again error, print the error, otherwise print the raw temperature value. And then I read, just as a matter of course, the period register. In case of an error I print the error, and then I print the content of the period register. I extended the print error function here a little bit so it prints the error as a readable text. Print status is also new. That just prints the 3 status bits nicely formatted. And the same holds true for print raw data, which just prints nicely formatted the data from our 3 axes here. And that's the output on the serial monitor. And let's see if I take that into my hand and turn it. Yeah, X, Y, Z values, they do change. Temperature does not change. Can we heat up things? Oh yeah, things are getting hot. So it's working, but let me copy the output here into a text file so we can go over it in our own time. That's a whole slew of data here, but I mean, we poll the registers of the chip every 25 milliseconds. We run for a few minutes, so yeah, it's supposed to be a lot of data. Let's first search for some errors, shall we? And oh, we have an I2C request partial in data read. And then we have the same in read period, read data, read period, read data, read data. And yeah, you probably don't see the scroll bar, but we're making quite some jumps here. So it doesn't happen every time, but it happens in between. Read period, read data, read period. Oh, there was a read status error. Partial in read status. Read data. Error in read temperature. Partial again. So, yeah, obviously we have I2C errors. But these are always request partial. Yeah, we'll keep that simply in the back of our heads. Now I want to show you a certain pattern here in the data. So we start out here in the first cycle with reading the status register and data ready is true. Then we successfully read the data and afterwards data ready is false. Then 25 milliseconds later, data ready is still false, and we're reading exactly the same numbers from our raw data registers. And in addition, we read here a temperature 0, which is interesting. Then 25 milliseconds later, data ready is still false. We still get the same numbers here. And only in the next cycle, data ready is true and we read new values here. Of course, only slightly changed. I didn't move our sensor around. And we also get here a temperature reading again. And data ready is of course after that read resetted to false, and it stays false for 1, 2, 3 more cycles until, yeah, the chip is only taking readings every 100 milliseconds. Data ready is true again, but we get an I2C partial error here, and obviously we weren't able to read the data. It's still the same values, but the next time the new values are in the registers, and they were probably in the registers here too, but we failed to read them properly from the chip. And then we have again false, false, and 2 or 3 more false. No, only 2 more false, then data ready again true, then false, false. We obviously, and that's by design, false, false, false. Now things get interesting. Again false, again true. So you see, we're polling the data too often. The chip only updates the registers every 100 milliseconds, so with 10 hertz. So that was really just to demonstrate you the function of that data ready flag here. Now I've changed the delay in the loop to 200 milliseconds. Let's have a look at the output. Now the output with 200 millisecond delay in between. And yeah, it's slower of course, but it's still working. This time rotating it across all the axes because I want to provoke something. I'm not telling you what, but you probably can see it on the screen. Anyway, temperature. Yeah, everything works fine. Let me copy that again into a text file, and then we have a closer look. Let's first see if we can find any errors in here. Oh, look at that, I2C partial request in read status. So there are few, but they are still there. We still have errors. That's interesting. Yeah, the important thing here is our data ready when we first just read the status register is now always true. Yeah, no exceptions as far as I can see. And of course, after we read the data registers, it's reset to false. And each time we get new values from our chip, because we are just reading now approximately every 200 milliseconds, while the chip is generating new data every 100 milliseconds. And also the data skipped is true because, yeah, we're only reading every second reading our little chip generates here. So overflow, data overflow, do we have somewhere data overflow? Oh yeah, here we had a data overflow. Not so good, huh? Yeah, no problem. We are at the 2 Gauss range. We can up that into the 8 Gauss range, and then this should be gone. However, the main problem I want to solve here is, of course, first we have to handle errors, and beyond just printing out there was an error. And second, I want to, streamline the communication here. And there is a 5th pin, you know, an interrupt output, data ready. Shall we use that? version 3 of the code. And I just made some changes to the sketch itself to implement the interrupt stuff. So first of all, I have a constant byte here, QMC5883L data ready pin, which is our pin 21. And I connected that pin actually to the interrupt output pin of the QMC chip. Then I have a volatile, because I'm using that in an interrupt routine, boolean data ready. Within the setup, I initialize data ready to false. Then I set my data ready pin as an input here. And then I attach an interrupt routine to it. Specifically to the pin QMC and so on, data ready pin, the function ready only for the rising edge of the signal. Of course, I implemented that interrupt routine, and I've done that before. And just to remind you, you shouldn't do a whole lot inside an interrupt routine. Especially don't try to do the I2C operations inside here. I just set the data ready to true. And then in the loop, I check if data ready is set, and if it's not set, I exit the loop immediately. Otherwise, I reset data ready to false, and the rest is unchanged. And of course, that works just fine. Yeah, we get still our reading here, but now the timing. The timing is determined by the interrupt pin from our QMC chip. Temperature, yeah, everything's fine. Let's just collect some data here and analyze it. So, first of all, we still have errors. I see here one right at the beginning at the I2C request partial in read period. Do we have more errors? So, yeah, we still have I2C errors. Not as many, but we still have them. Okay, so next. Data ready is now obviously always true when we start our cycle in the loop, because the chip just told us via that interrupt signal that data is ready. So in theory, we could just forget about that first reading of the status register here. Yeah, it's obsolete. Data skipped is also always false. Let's see if we can find a data skipped true. Oh yeah, there we have 1, 2, 3. So in between, it seems our Arduino is a little bit too slow, even at this 10 Hertz pace, which I almost can't believe, but yeah, it seems to be. The status register says data skipped true, or maybe we are missing interrupts in between. Interrupt signals too fast for the Arduino. I don't believe that either. Anyways, yeah, that's it. Let's try one more thing. So I've set now in the config the output data rate to 50 Hertz. So data every 20 milliseconds, an interrupt every 20 milliseconds. Just to check if we get now more data skip warnings in that flag here. And of course the data is now coming much faster, 5 times faster. But yeah, turning that stuff here, heating up the temperature sensor, everything works fine. Let's have a detailed analysis of that data here. You know the drill. Let's first search for errors. Oh no, let's first search for data skip true, because it's already there. Data skipped true. And yeah, there's an error. Yeah, we're still skipping data. Honestly, I have no idea why. Maybe the Arduino is really too slow? I don't think so. Who knows? Maybe you have an idea. Anyways, that should be enough for today. First of all, I have to think how I want to implement the error handling within the library, or if I want any error handling inside the library at all. Would be nice because, yeah, these errors we're experiencing are probably recoverable. Just, yeah, repeat the operation and you probably get the data back from our chip here. But next time I want to talk in detail about calibrating these chips. Yeah, we already learned in the basics card here, link in the description, that without proper calibration, the data returned by these magnet 3-axis compasses, digital compasses, is basically useless. So we need calibration, and that we shall do next time. Till then, bye.